If you've seen some of my previous videos, or if you're familiar with the field of natural language processing, you shouldn't be surprised when I say that machine learning models, at least those trained for NLP, aren't really that great when it comes to math. This has actually been a pretty central part of one of my main criticisms of these large language models in the past. But what if you take one of these large language models and you focus on just math with much more math specific data and more careful math specific data processing? Well, that is what this new paper out of Google takes a look at, and the results are pretty impressive, even going as far as being able to solve some university undergraduate level math problems. So if that sounds interesting to you, take some time to join me for this paper. Solving quantitative reasoning problems with language models just recently came out of Google Research, and I think it's a paper with some interesting results. In this paper, the authors introduce a new model called Minerva. It isn't that different from previous models, but there is new stuff they do in terms of how they process the math and stuff, and the results are definitely new. And as I mentioned earlier, this can do some level of undergraduate level math, and not just math. We actually look down here and it says they evaluate on 200 undergraduate level problems in physics, biology, chemistry, economics, and other sciences that require quantitative reasoning skills. And that isn't to say that it will be able to solve all of these, but it is able to solve some of them, and to what extent? Well, nearly a third of them. So it's pretty impressive. We can actually take a look at some of the example problems. Actually, just scrolling down to get us started, we can take a look at what we're going to be seeing from this model. So here's an example of, a question. So a line parallel to y equals 4x plus 6 passes through the point 5, 10. What is the y coordinate of the point where the line crosses the y-axis? So you can see this is actually pretty neat because there's some natural language in here, and I can scroll down a little bit more. There's some natural language in here. This goes beyond just pure mathematics. It actually has word problems. As a matter of fact, I think actually the majority, if not almost all of the examples we'll see are word problems. And you can see that the model output, so the target here, this is what the model should be predicting, this thing right here. So this would be the sample answer. Since the line is parallel to y equals 4x plus 6, we know that its slope is 4, blah, 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 and you end up getting this answer of -10. If we actually look at the model output, we can see it says the line is parallel to y equals 4x plus 6, which means that it has the same slope as this equation, which is true. That's the definition of something being parallel, right? Since the line passes through 510, we can use the point slope form of a line to find the equation of the line. And you can see it actually writes out its steps here and explains its answer and does come to the right answer. So this isn't the hardest question ever, but regardless, it's not like it's a super easy question, right? You do have to understand a little bit about what's going on here, especially because it's in the context of natural language. So you'll see it does some problems that are easier than this, some that are harder than this, but also messes up in some weird places too. So we'll be taking a look at all of that. Also, a quick aside, if you like this type of content, I do a whole lot of, covering big papers to keep you up to date, and also covering some smaller, interesting ideas to, introduce you to interesting ideas. So if this sort of thing interests you, do consider subscribing to the channel. It really means a lot. Thank you so much. Back to the video. We can get started by jumping down to the paper's contributions down here. So what do they say here? So we present Minerva. This is what they call their model. It's a language model that achieves strong performance on many quantitative reasoning. That's what we heard. One thing that I think is kind of funny is not funny, but it's impressive, is that they do all this in LaTeX. Correct. So they actually use LaTeX notation, LaTeX, not latex. This model is, I'm pretty sure, better at writing LaTeX than I am. That's kind of funny. Not that I'm very good at writing LaTeX, but if you're not familiar with what LaTeX is, well, it's a very common format that you'll see, a sort of way of writing down mathematical equations. And this is, if you're writing up a PDF, like a paper or something, this is the format that you use to write certain equations. So we'll be able to see what it looks like, but it has like a lot of slashes and then like this sort of thing. And then honestly, I'm completely forgetting right now because it's been a long time since I've written any LaTeX. Or at least a couple months. So we'll see as we scroll down, though. You'll get to see some examples. In terms of the actual architecture of Minerva, this is based on PaLM. It's based on PaLM, which is, I think it's around 400. Oh yeah, it says right here, 540 billion parameter pre-trained model. So it's an NLP model. This is also released by Google. Their pathways based model, and they train actually 3 different models. So one that's 8 billion in size, 62 billion in size, and then the full model, as I just mentioned, is 540 billion parameters. So the actual architecture, as far as I'm aware, is not different at all from PaLM. The difference is actually just in the data, and what we'll see is that by training on these different types of math problems specifically after the pre-training on general data, you're able to get much better performance on math specifically. Now, I don't think that's a big surprise. It should, if you're familiar with this sort of thing, it's pretty well known that fine tuning on a specific area can really boost your performance there. But maybe or maybe not, you'll find it surprising to the extent it actually is able to improve. If we scroll down to the next part here, I guess we have a few more examples. There are lots of examples. Let's go over a couple more though. I think it's fun to see what the model actually is capable of. So in this one, we have assume that the variance of the first in natural numbers is 10 and the variance of the first in even natural numbers is 16. Compute in plus n. Okay, so this is interesting. So natural numbers are like, I believe, positive integers. So like 1, 2, 3, and so on. So this is not like a very easy question, as you can see. I think the model gets this right. Let's check. So example left. So this is from the joint entrance examination, main math 2020 exam, taken each year by almost 2 million Indian high schoolers. So this is like high school, but going into, I guess going into college. This is interesting. So it's clearly not a simple problem. I believe, it doesn't say if this gets it right or not, but I'm assuming it gets it right or they probably wouldn't be showing this example. And then this one, I actually solved this one on the right in my free time just to make sure I could solve some of these. Essentially, you just have an equation and it asks you to prove that A is not equal to B. And this is sort of just a very straightforward proof. A very straightforward proof. I say straightforward. If you don't know math very well, maybe it's not straightforward, but in the sense that you just kind of, you mess around with the equations. This one's much more math-based and less natural language-based. And you can see that the model is able to do both of these quite well. So after PaLM is pre-trained, which I guess has already happened in a previous paper, right? PaLM is, if you want to look into that, I know they have a paper out about it. You can, I'm sure, find some videos on YouTube too. But after the pre-training is done, once they do the actual training on the more technical mathematical data, they use a few data sets. So, and these are for evaluation. One is math. I believe this is a combination of both middle school and high school data. Then they have the GSM 8K. I believe this is middle school math problems. And then they have the STEM subset of the MMLU dataset. I've talked about this in some previous NLP videos, and it's essentially just a conglomeration of a bunch of different natural language tasks. And this includes some of what we saw earlier, right? Just straight up math. It also has some physics, and it also has some questions in a few, these quantitative reasoning areas that we'll probably also see as we go. And if we come down here, we can see that this is new. They have an undergraduate level questions data set, as I mentioned earlier. So this is from MIT Open Courseware is where the questions come from. And it's a mix of science and mathematical questions. That being said, even though there are some science questions, I believe all the science questions are, at the end of the day, they involve using some equations. They're not just like word problems. They actually require you to do some sort of math. So they are all math-based to some extent, though there is a little bit of a mix in there. Going down to the training and evaluation section, now we're going to start getting into more of what's in this paper specifically. And although I already mentioned some of the data sets that this paper uses, the math data set and some other ones, the actual data set they use for training the model is different. What I mentioned before, the OWC data set, the math data set, the GMK8K or something like that, those are actually just for evaluation. The actual training data set, and I think this is pretty cool, is primarily archive data. It's a mix of archive data and math that's just filtered from web pages. So they scrape the web and they get, 38.5 billion tokens. And all of those tokens are from archive papers that have math equations. So archive papers, these are just normal research papers, right? But they'll scrub them and they'll search for the math content. And then they'll also do the same for the web. They'll go through websites and try and find math and then take those equations or those problems that they find and use those as the training data. This isn't really too different from what you do in any sort of like normal large language modeling, but I think it's neat to me maybe because archive papers tend to have math that's very difficult to understand because these are usually, going to be papers that are on the cutting edge of whatever they're doing. And because of that, the math tends to get pretty complicated. So the fact that, as we'll see, they have some pretty good results and they can get those results partially by training off just like archive and web pages, it's pretty impressive. They do talk a little bit more about the formatting of the math and stuff here. It removes like HTML tags. They do all sorts of pre-processing. We'll skip over that. One thing they make sure they mention is that one difference from other sorts of papers that use natural language processing is they make sure that they capture all the different mathematical symbols that are being used that are often, kind of thrown out by other models because they're not very common tokens. Well, they make sure to capture all of that. See here, they say they preserve mathematical notation, including latex symbols and formatting. And they give a few examples and some more details in the appendix, but I think you get the point, so we'll move on. The actual breakdown of the training data they end up using is about half math web pages and half archive pages, and then a little bit of general natural language data. So this is going to be stuff that isn't necessarily math, just some normal natural language. So that covers the data. Next thing we can get to is the actual model and the training. So I've already mentioned this. They use PaLM. The PaLM pre-trained decoder only transformer for language models. And the idea here is that you start off with PaLM. So I'll just do P for PaLM, and you put in a bunch of pre-trained data. This data is just going to be mostly just normal natural language. So you might get a bunch of web pages and a bunch of God who knows what. So that goes in, and this is the very standard NLP task of you're just predicting the next token. So maybe you see I walked my, and then you have to fill in the next word, or at least the model has to do that, and you might predict something like dog. This is very standard. But then they take this pre-trained model right here and they go into stage 2, and stage 2 is, well, it's the same thing. They have P, or the PaLM model, but now they're feeding in a bunch of different data. So the data going in now is a bunch of math data, and this is the final part of the training they're doing. So this is doing the exact same thing, right? You just have something like this though. You have 8 times 3 equals, and then it will have to predict the output from this. So the model will hopefully, in this case, predict 24. And I'm not going to spend too much longer on this because, well, there's really not much new happening here. As I mentioned earlier, the sort of novelty of this really comes from using a different type of data rather than a different type of model. The model, as we'll see, already works pretty well. The next thing after this is the evaluation data set. We already talked a bit about this though, so we'll skip on ahead to the results. The first thing that the results take a look at are the math data set and the MMLU evaluations. When they are doing this evaluation, they do a 5-shot prompt per topic. So each of these math and MMLU data sets are split up into different types of topics like physics or engineering. I guess engineering is a bit broad, but you know, that sort of thing. And by 5-shot prompt, what they mean is that when they're asking the model for, or they're prompting the model to get an answer, they'll give it some context. So the context will look something like this. It will be Q1, and then part of Q1 will be, you know, if like x plus 6 equals y, and it will be solve the equation or something like that, right? And then it will have an answer, and there will be an answer here, right? So I guess this doesn't actually have an answer. So maybe solve for x would be the question. And then we would get, you know, what would it be? X equals y minus 6. And that would be an answer. And then they would have Q2. Obviously, the problems I think are harder than this, but the idea is that you prompt the model with 5 of these different questions, you feed these into it, and then you give it the final question. So question 6 is going to be the actual question. And once you give the actual question, it then gives you an answer, and that answer is what you use as your final answer. At least that is one way you could do it. They also do one more thing. So they'll do this maybe 16 different times. So this is another thing they do. They do majority voting. So we sample k equals 16 model answers using a chain of thought prompt. So in this case, they'll prompt the model for 16 different answers, and then they'll choose the best one of those. And I'll talk very briefly in a bit about how they go about choosing that. And you'll see in the evaluation we're about to look at, they try this in 2 different ways. In one way, they just do a 1-shot. So they'll give it the 5-shot prompt and then take the first answer it gives as the final answer. And in another case that they evaluate, they do this, but they get 16 different answers and choose the best one. And we'll see how those compare. Here's the results. So what are we seeing here? So first we have on the math subtopics, or let's highlight that instead. Accuracy on math subtopics, and then on MMLU subtopics. So you can see that the math data set and the MMLU data sets, they're each split up into different categories, which we can see down here. So this is a mix of math related areas like probability, geometry, algebra, and then in MMLU, we have chemistry, math, physics, and so on. And what we're able to see here is a comparison between PaLM and Minerva, and then different versions of both, and then also a different baseline from OpenAI. So there's a lot going on here. So let's go through these one by one. So let's start by just looking at the 8 billion parameter models, because that's how this is organized in these graphs. They're organized by the number of parameters. So if we look just at this 8 billion parameters, we have PaLM with 8 billion. So this is PaLM without any math fine tuning, just the pre-trained on natural language data. Then we have Minerva at 8 billion. So this is PaLM after it's been fine-tuned on all this math data. And then we have Minerva 8 billion, and then this majority, MAJ, stands for majority 1 at K. And that essentially means instead of doing a 1-shot, Minerva is able to generate a bunch of candidates. So if we have our Minerva model, it will generate possible solution 1, possible solution 2, possible solution 3. You generate k number of solutions, and then from all of these, there's a voting system that takes place, and just one of these is chosen to be the final answer. The actual way the majority voting works here is through a method called, I believe it's nucleus sampling, which is very similar to just choosing the answer that is the most common, or at least an answer from a set of answers where that sort of set of answers is the most common. I think I'm sort of bastardizing this a little bit, but it's something like that. So now if we actually look at the performance of all these 8 billion parameter models, so this is all the way on the left of each of these sort of purple areas right here, we can see the dark purple is the performance of Palm. And then as we get lighter, we can see the performance of Minerva. And we can see that in all these cases, Minerva is performing better. Now, this really shouldn't be a surprise, right? Because Minerva, after all, was trained on math-specific data. I guess perhaps what the takeaway here is how much you gain from that math-specific training. It's not really an insignificant amount. In some cases, we can see like around a 20% increase. In some cases, we can see, I think the smallest improvement we see is around a 10% increase. So there's like 20% here, 10% here, and all that I would say is, it's pretty substantial. If you actually look at the x-axes of both of these, of the math subtopic dataset and the MMLU dataset, you might notice that the MMLU one is overall higher, with the average somewhere around like 50%, whereas the math dataset is probably closer to like 30%. Part of this reason is because the MMLU data is actually multiple choice. So it is a bit easier to get the problems right. But regardless of that, we can see that overall, Minerva is still performing quite a bit better. So what happens if we look at now the larger models? So we'll just skip over the 62 billion parameter models because really the same trend holds. And if we just look now at the 540 billion parameter models, which are the biggest, we can see this is actually where we see the biggest improvement. So on the right of each of these, the lighter colors, you can see that this is where Minerva really significantly outperforms Palms. So you can see in each of these, the performance increase is from here to here and here to here. Or if we look over on the right, from here to here, it's pretty significant in most of these cases. A little bit less so on the MMLU dataset. Maybe that's because of the multiple choice questions. And even if you take out the majority voting, we're still seeing quite an increase. That would be from here to here, here to here. So usually at least like a 10% increase for the math subtopics, and then for the MMLU subtopics, a little bit less. And then the last thing they compare to, or the last two things they compare to, are the published SOTA previous to this. And you can see on all of these, they're essentially outdoing the SOTA. So they're state of the art, which is, that's great. The model they're using, I think, is also bigger. So that's also part of the reason. And then they also compare with OpenAI DaVinci. I forget if DaVinci is just a general NLP model or for like programming or math specifically. But regardless, they do show a comparison there, which you can see it's performing fairly well, I think better than Palm, but still not as good in any case, not better than Minerva. So Minerva is undoubtedly, the best here. It's not really even close. So what about the results though on the other data sets? So the next thing we wanted to look at, right, was these undergraduate level problems. So that's what they're taking a look at right here. So these types of problems, just like the other two data sets previously, are not pure math. They give some examples here of what we'll be looking at. So solid state chemistry, which I don't know solid state chemistry. Information and entropy. If you do ML, you probably know a bit about that. Differential equations, special relativity. So there's some of that physics. And they actually hired contractors to make these problems, or to essentially go over these problems and make sure that they put them in a format that is self-contained and clearly delineated final answer. So this is to sort of avoid, these problems that might either be vague, or they might require you to go to a textbook and look up like some image. If that sort of thing was the case, well, then those problems were dropped from the data set. So this is hopefully, I haven't looked at the problems myself, but they should be a fairly clean set of problems that the model should be able to solve if it, has properly learned what it's been trained on. Overall, there's 272 of these problems, and they break that down to two categories. 191 of them have numerical solutions, so that's just going to be the answer is going to be a number, and 81 have symbolic solutions. So that would, I guess, be something like an equation, like saying x is greater than y or something like that. That's that's a fairly simple example, but something of that form. Scrolling down, we will find the next evaluation that they show us. And this is a little bit of what we saw before, but also more. So the math and the, where is it? The MMLU STEM. This is what we already saw before, but now in table format, right? So you can see for each of the 8 billion parameter models, and I can do this in like red, each of the 8 billion parameter models, you can see the percent it got right. So this is the percent it got right for the best model, the one that generates 16 different answers and then chooses the best one. Then you can see here for the 62 billion parameter model, and finally the 540 billion parameter model. And what's new here is that they're also including the OCW courses and the GSM-8K. So the OCW courses is probably the most interesting thing here because this is the undergraduate problems data set. It's simply going to be the hardest. And you can see that the final performance it achieves is 18% for one shot. And then if you do the 16 problems generated and then choose the best, it gets about 31% accuracy, which, I mean, that's pretty impressive. I don't think all these undergraduate problems are the hardest undergraduate problems, but a fair bit of them are. And it does solve some fairly difficult questions that, at least from what I was looking at when I was looking through some of the examples. You can see this is a pretty significant performance over OpenAI's DaVinci. I mean, I'm not sure if DaVinci was trained on the same sort of math data. I'm forgetting right now, but regardless, it's over a double improvement. So pretty good. Now, if we scroll back down the results and look over a little bit more of what they were saying, they included one more section about basic arithmetic. So this is actually kind of funny. And they say if we look at Appendix H, which we're going to go to in a second to take a look at, the model achieves over 80% accuracy on 10-digit addition and over 20% accuracy on 18-digit addition. So you might think, wait, what? It can't do addition, but it can do all these other very difficult things. And if you're confused by that, yes, that's exactly how this is working. And this actually isn't too surprising if you've seen similar papers that look into this before. So let's scroll down to the appendix real quick. And here we are. Right here, you can see for addition, subtraction, and multiplication, they test all these differently. As you add more numbers, and we go to the right on this x-axis, as you add more numbers to the addition, subtraction, or the operation that needs to happen, the accuracy actually drops. And this is kind of interesting, maybe if you haven't seen this sort of thing before, right? You might be thinking, why can't it do these simple things if it can do these much more complicated questions that require complex like equations and understanding of natural language? And really what this is showing is it's showing a lack of generalization. The reason humans are able to do these sorts of, having many digit addition. So if I have like 1, 2, 3, 4, 5, 8, 2, 1, and then I add that with, something else, the reason I as a human can do that so well, and I guess here that would be like, what's that, or 8 digits. So even the model can do it fairly well. But if we keep adding digits, it doesn't get that much harder for a human. The reason it gets harder for the model though, is because these types of numbers are not in its training set, right? There's very few things you're going to see online where you're trying to add like 20-digit numbers because, no one cares, because everyone, if you know how to add 5-digit numbers, you know how to add 20-digit numbers. It's the same process because humans they can understand how addition works, and we have a rule-based system, and that's kind of, I guess, the key word there. We have rules for how to do these things. We have algorithms that we follow, and if you follow those algorithms, you will always arrive at the right answer. Now, current models, as far as I'm aware, I mean, unless you work in rule-based AI, machine learning language models, they don't have these sorts of rules. I mean, maybe there's some sorts of rules you can extract from their weights, and I think there are some papers that look into that, which is a little bit interesting, but they don't learn these sorts of algorithms, or at least this is sort of pointing to that, right? And this shows the extent of generalization of models, at least right now, for these types of problems. And I think although the previous parts of this paper have sort of maybe weakened my criticism to these large language models somewhat by showing they can do quite a good bit of math, this maybe strengthens my criticisms a little bit by showing that there really still is, even with these huge models, 540 billion parameter models, there's still this very clear limit to things that are outside of their training distribution. They are doing out of distribution generalization to some extent, but the extent is limited. I'm not sure how we're going to solve this or how the field is going to solve this, whether it is by implicitly, making rule-based agents. I probably don't think that's the solution, or maybe constructing architectures that can learn these sorts of algorithms. I know there actually is some work in that area that I find really interesting, though I'm not super familiar with it. I think there's a lot of possible avenues here, but this is a great place to look to improve our models. This is a great like motivation, right? And this isn't a new problem. I think other papers have looked at this too and found the exact same thing. And as we keep scaling up models greater to be bigger and bigger, they will keep getting better. I have no doubt. But I think it's things like this that show that maybe that won't be all, that maybe that won't be enough. If we scale up to a trillion, 5 trillion, 10 trillion, 100 trillion parameters, and we're still seeing issues here, I mean, I think it'll get better, but how much better? I don't know. It won't be perfect, right? It won't be perfect, but humans can do this perfectly, and I think that's an important thing to mention. And again, that's not to take anything away from this paper. It's not really a criticism of the paper. I'm glad they addressed this. It's just something to think about. So we came back up to the main part of the paper here, and now here they go into a bit more of an analysis of the results, which is great. It's good to take a look at where the model is not performing well, to get some motivation as to how they can improve it in the future. So here in this section, they're not just taking a look at model mistakes. They take a look specifically at model mistakes of Minerva 8 billion compared to Minerva 62 billion on 216 different problems. And what is this? So, and they do this with high confidence majority decisions on both models. So they look at specifically problems where the models were very confident that they had the right answers, but the smaller model did worse. They were wrong, well as the bigger model was correct. Why might this be interesting? Well, this is interesting because it shows us what scale could potentially help with, right? It shows us as we scale up the model, these are some of the issues that the model is, or that the scaling is helping with. So the biggest one is incorrect reasoning, then incorrect calculation, then misunderstanding a question, use of incorrect facts, solution are too short, hallucination of math objects. And can I just talk about for a second how hilarious this hallucinating math objects is? Like, imagine I have to solve the integral of, I don't know, like x squared plus cosine of x. And then I like forget how to do this. So I just make up my own rule how to integrate this. I don't know if that's exactly what this is referring to. Maybe that would be incorrect fact, and hallucinating math object is just like putting something in for convenience. Anyway, it's kind of funny. But the majority, those problems are on the fewer side, right? I guess the incorrect reasoning and the incorrect calculations are the big ones here, which I guess means that increasing in scale in these cases was able to help. And we shouldn't say that this will always help with reasoning, but it was able to help with reasoning in many cases, and these calculation errors in many cases too. So it is interesting to see good motivation to scale up, you could say. Now, they also talk about false positives, and in this case, they mean false positives as in the model gave the right final answer. However, the actual reasoning of the answer, and I think they say this here, where is it? Yes, we do not have an automatic way to verify the model's chain of reasoning, right? Because it's natural language, which means there might be false positives. So they have the correct final answer, but the reasoning is incomplete or incorrect. And I'm sure some people have some mixed opinions with this. If you've ever taken a math course or more than one math course in your life, just in middle school or high school, you will know that different teachers have different ways of going about this. Some are like, you got the final answer, full points. That's, at the end of the day, if you get the right answer, good for you. And then some will say, if you don't show your work, it's 0. So I guess the stance of this paper is that the chain of reasoning is very important. And I guess I somewhat agree there, right? Because if the chain of reasoning isn't right, then it's probably not an accurate way to measure the performance of the model. You're picking up some randomness, I guess, in that sense. Although maybe you could argue it's not entirely randomness. Maybe it is learning something, but I don't know. It's hard, but it's one thing they look at, and we can take a look at this. So they look at the false positive rate per the difficulty of the actual question. You can see as for difficulty levels of 1 through 3, which are the lower difficulties, there's not too many false positives, 5 to 10% or less than that, 0 to 10%. Not too bad. But then once you get up to level 4 and level 5 problems, these get a lot more frequent. So 15 and 30%. That's not great. So it shows maybe the more difficult problems, it's definitely having a harder time solving. And the few times it does, there's not the majority of the time, but there's an okay chance that it might have been a false positive. And I guess that shouldn't be too surprising, right? Harder problems are harder to solve. And one thing they mention here, and this is part of the reasoning of why they do what they do, is in order to lower this false positive rate is that they use this, where is it? So they have pass at 1. This is just a one shot, right? They throw in the 5 prompts or the 5 questions of a prompt to make a prompt, 5 questions to make a prompt, and then they get one answer out and use that, or they use majority voting, which is what we talked about earlier. Previous works, not all previous works, but some previous works, so AlphaCode, for example, which was a paper by DeepMind that writes code, uses a pass at k mechanism or method of calculating correctness. And this is, I'm not a huge fan of this. What this means is that we're going to generate, so k answers. So in pass at 256, that means we're going to generate 1, 2, 3, 4, 5, all the way up to 256 different answers. And then if any one of these is right, if a single one of these is right, then that means we're counting that as a correct solution. That's not what they do in this paper, which I think is a good thing. I don't love pass at k because you're essentially, the more you generate, the more likely you are to get the answer right. But there's no way if you were actually using this model in practice to know if your answer is right, which is not great. And they say that if you do use this pass at k form of like accuracy, you end up getting, do they say they suspect you get more false positives, or do they actually test this? False positives account for part of it. So yeah, I guess what they're saying is that that metric is not only bad because you can't figure out which of the answers is correct, but also because of the fact that it's worse for false positives. So another thing that they look at, and again, I'm happy they look at this. This is one thing about this paper. I think they're looking at lots of the right things in the evaluation, is memorization. Memorization is very key because I think a lot of people are sort of opposed to these sorts of large models because lots of times they say, well, it's just memorizing and interpolating between different answers. And it's kind of hard to figure out whether, what exactly is going on. I think to some extent we have some sort of memorization going on, but the real question is it memorizing just like pure answers that it won't be able to extrapolate from when it has new types of problems, or is it memorizing in a way, maybe memorizing some of the key facts that can be reused? Maybe they don't go that in depth in this evaluation, but they do look to see if any of, I think, the questions or answers, if they're just copied or very similar to things that were in the training set. And this could be a big issue because remember, the training set was just a bunch of data from the web. So it wouldn't be surprising if they see some of the same problems repeated in these test data sets, because, if you have these problems in these test data sets, it is very possible that people could have gone to the web and asked for solutions for these exact questions. Or you could just get, if you have simple problems, you could end up with very similar problems. So if we scroll down here, we can actually see, and here they talk a little bit about the data set overlap. We're going to come back to that in 1 second, but first I want to take there we go. First I want to take a look at the performance on modified math problems. So what they do here, they randomly selected 20 problems for the 62 billion parameter model, answered correctly under majority voting. Then they manually modify each problem and introduce minor changes to the problem wording or changing the numbers which appeared in the problem, and modifying the solution to fit the new question too, of course. And then they compare the accuracy over these new problems compared to the old problems. So just to reiterate that, they start with one problem. So they start with question 1 and answer 1. And then they do one of two things. They either, I don't have much room to write here, but I can do this. They either change the numbers or they change the wording. And then they see, can the problem or can the model still solve this, or is there any correlation, right? So one thing that would be alarming is if they change the numbers by a little bit and all of a sudden the performance of the model dropped a lot, or if they change the wording a little and the performance dropped, that would be a big red flag. And here, if we take a look at this is where they're changing the framing, and in the middle here, this is where they're changing the numbers. They can see there is some correlation between the accuracy of the original and the accuracy of the modified problem, which is good. We shouldn't see, if all the dots were on one side of this line, that would be a big error. But instead, we're not really seeing that, right? We're seeing that there is a correlation here. Although I will say that for the modified numbers, there is a lot of variation, which is, I think, one area for improvement in the future, right? Ideally, if you just change some numbers in a problem, if it's generalizing well, it should be able to still solve the problem without much variance. However, we can see here that there actually is quite a bit of variance. If they change the wording of the problem, so the actual wording, it doesn't change much, but the numbers do, which means that the model is very much more, is somewhat invariant to problem framing, but not so much to the numbers that are used, even though it probably should be. And I think, again, this is in potentially somewhat of a generalization issue. I'm kind of throwing that word around here like a buzzword at this point, I feel like, but hopefully you get the point I'm going for. One more thing they do is in this majority voting accuracy with filtered samples, essentially here, let's see if they, I think they explain it down here. So we seek to detect memorization by computing the blue score. Oh, let's go back to highlighting and undo. Oh gosh, oh my gosh, computing blue score between ground truth answers and model generated answers. So the blue score is a measure of similarity. So if I have two sentences, this is a, and I'm running out of time here, so I'm just going to abbreviate this. This is a, and this is a, and these are the exact same sentence, then this is going to give me a blue score of 100. If I change one word, so I just remove the word is, this blue score is now going to drop. How much it's going to drop is going to depend on how many other words there are in the sentence, but maybe it would drop to something like 80. I don't know. But the point is, the higher the blue score, it's a scale of 0 to 100, where 0 is not the same at all. No, in other words, none of the words are the same. It's a comparison of how many words are similar. So it's a very rough measure. And then 100 is exactly the same. So they're essentially comparing the similarity of the answer, at least in terms of the actual words used, the ground truth answer to the generated answer. And then what they do, and this is kind of interesting, they compute the overlap statistics for all correct samples and find that 160 out of 5,000 test questions have a sample with a blue score of greater than or equal to 80. So this means that 160 out of the 5,000 answers are very similar to they're almost the exact same as the ground truth answers. So the question that they're going to be asking here is, if they remove the model samples above a certain blue score threshold and recompute the majority vote accuracy, will this change? How much will this change the performance of the model? In other words, if they take all the cases where the solution the model gave was very similar to the actual answer, so if they take that answer away and make it give a different answer, can it give an answer that's maybe worded a bit differently, but is still correct? And if we scroll up, that's what this graph earlier was showing. So here is like the cutoff for 80 an 80 blue score, right? So if we look here, what this means is it means that if we take all the answers out, so those 160 answers that were very similar to the ground truth answers, and make the model recalculate the overall accuracy, how is the accuracy at that point? We can see that it doesn't drop very much. And we can see that it doesn't really start dropping too much until around the 40 to 30 blue score range. And you might be thinking that this is very good because 30 to 40, that seems like not very similar, right? And if you're not familiar with blue score, that's probably what you think. But let me pull up a little thing here. And this is from Google themselves. And this is how you should look or think about a blue score. And again, a blue score is a very rough number, so take this with a grain of salt. This only works when you're looking at like lots of different, you're looking over a corpus of data and not just like a few examples. The blue score for like one or two examples means very little. So in this case, over 160 different cases in the 80 blue score case. I'm not sure how, it's probably enough, but it does definitely have some noise. But anyway, getting back to this. Less than 10, useless. Up to 20, not too good. Up to 30, kind of similar, but still not that great. Up to 40 is okay. Up to 50 is pretty high quality. Up to 60 is really great, almost like very similar. Same thing, basically. Over 60 is basically, this means better than human. And what I should mention that blue score is usually used for translations, not this sort of comparing two sentences for mathematical purposes. So, it's good to know. But this is interesting, right? Because when we look at this, we should actually probably say around closer to 40, not 80, but closer to around 40 would be the cutoff to where things are very similar. I don't know. It's kind of hard to say because I guess at the same time, if you have something that's at 40, the two sentences are going to be somewhat, they're going to be quite different, but generally the overall meaning is going to be retained. But I'm not even sure if that interpretation, how well that transfers over to this mathematical case, because changing like one symbol in math can be a big difference. So I'm trying to point out here, let me go back to the thing. I'm trying to point out here is that it's pretty hard to interpret this. And I don't think, they point this out as a very good thing. I don't think it's that easy to say that this specific graph is a very positive thing. I don't think it's also easy to say it's a very negative thing. But anyway, take that as you will. Now you kind of know what the blue score is, so you can hopefully make your own judgment on that. Honestly, I'm reserving my judgment on this, but overall, I think this was an interesting thing to look into. So that's really the last thing here. I mean, they do have an appendix too. I think this is overall like 40 or 50 pages. If we scroll down, there's a lot more examples that you could take a look at that I think are pretty interesting. They also just put some straight up code in here. As you can see, there's quite a lot. But what do I think of this paper? Hold on, wait, I'm going to scroll down. I know they have examples here. It must be at the very bottom. Oh, we already looked at that. Yeah, here's where the examples start. You can see if you scroll down, you can see some of these are really long. And there's some pretty tough questions. So do feel free to come down and look at these on your own. They also give some examples of some incorrect reasoning, different sorts of modes of failure here. They have an incorrect calculation one where it just takes off the square root. You can't do that in math. So there's some interesting things happening here. If you want a better idea of how good it's actually doing on these questions, come take a look at this. It's definitely interesting. What do I think of this paper though? I like this paper. As I mentioned at the beginning of this paper review, I have criticized LLMs, large language models, for using for math and these sort of reasoning tasks quite a bit. I don't think they're the best. And I think this paper didn't change my opinion all that much, but that does not mean that I don't like the paper. Because I think although I criticize LLMs and I say that I don't think they'll be able to solve all these different math equations, it is very much possible that I'm wrong. Totally possible. It is possible that we just scale up enough and everything works, but I don't think that's the case. And I think this paper somewhat supported that, looking at things like the numbers and stuff. But then again, it did get better at some other things. So it's definitely not conclusive. I think it was interesting to see, if you focus specifically on math data, how that alone will impact the model performance. And overall, I think the evaluation was pretty good. I think they looked at the right things, making sure things weren't memorized, or at least looking into how much things were being memorized and that sort of thing. Overall, I think the paper is pretty solid. It was an interesting read, well put together paper, and kudos to the authors. Anyway, I hope you enjoyed this. If you did, consider subscribing. It really helps out. Thank you so much for watching, and sorry if this was a bit faster than normal. I gotta head out right now, so I'll catch you guys later. Thank you so much for watching, and I hope to catch you next time.